It turns out that there are quite a few properties that depend on the concentration of a solute in a solvent. And these are known as colligative properties. And I'm listing here some examples. So the boiling point of a liquid, we think of it as a pretty set number. But if one dissolves something in the liquid and makes it into a solution, the boiling point of that solution takes sort of like a weighted average of the two, and it tends to boil. So for example, salt boils at a much higher temperature than water would, and if you were to add salt to water, the boiling point of the solution would be higher than 100 degrees Celsius, and of course far lower than that of NaCl, but even still it increases it ever so slightly. The freezing point is usually diminished by adding a solute to a solution, because the freezing point of most solid solutes are far lower than that of the liquid that they're dissolved in. We also have an effect on vapor pressure and osmotic pressure, and we'll discuss what they are in a bit. But let's first focus on the boiling point and freezing point. And the equation is quite similar for the both of them. The change in temperature of boiling is equal to this factor I times this factor K times the molality of the solution. Molality, not molarity, but molality of the solution. K is specific to solution liquids, to the solvent, and it's provided in any question you may be asked. And I is the number of ions that the solute produces when it dissolves in the solvent. Okay, and this delta T is how much the temperature, the boiling temperature, increases by from the pure solvent. And same thing occurs here in the freezing point. Here you have to subtract it from the initial temperature. And still, I is the same, K is provided to you, and M is the molality of solution. So let's look at some examples. I think they would really help you understand it a little bit better. First, let's discuss this I factor. I said it's the number of ions that form when the solute goes into the solvent. So let's say I have NaCl going into water. Well, NaCl will produce Na plus and Cl minus. And if you count them, there's two of them. So I is equal to 2. Okay? When I put water in water, well, water in any liquid, water does not dissociate, so it just stays by itself, so I would be equal to 1. Carbon dioxide, same thing, it does not dissociate, so I is equal to 1. So if it's not ionic, I is equal to 1. If it is ionic, you just have to count how many ions you're forming, and that's what I is equal to. Here, as you can see, I form 2 lithiums plus 1 oxygen. So my I is 1 plus 2, it's 3. Okay? Here I have aluminum forming and 3 hydroxides. So my I is equal to 1 plus 3, and that's 4. Okay? Fairly simple, understandable. And so let's see what happens now in an actual question. Let's find the freezing point of an aqueous solution of sucrose, which is sugar, table sugar, containing 25 grams of sucrose, which is this, for 100 grams of water, and I'm giving you here the Kf. And to remind you, the equation right here, I'm talking about the freezing point, so it's this thing. So I'm going to lower my freezing point by how much? So I have delta T of freezing is equal to negative I K freezing times the molality of solution. And I give you K sub F. I for sucrose, as you can see here, this will not dissociate. I is equal to 1. We're looking for this, and we're given kind of this. We have to find this in a more agreeable notation. So we have 25 grams per 100 grams of water. So let me just write that down here. we're going to convert this to molality. 25 grams of sucrose per 100 grams of water. And to remind you, molality, I'm going to write that here, it's mole of solute divided by the kilograms of solvent. So I have grams of solvent. Let me just convert this to kilograms. So I'm going to have 1,000 grams for 1 kilogram. So that takes care of this. So now I have a kilogram. Great. And I got to make this into moles. So I need to just get the molecular weight for sucrose, which is 342.3. So I will just convert that to moles. So 342.3 grams of sucrose per mole of sucrose. Okay, and once I complete that, I should be able to get my molality directly. And indeed, this ends up being 0.730, little m for molality. Okay, so now I got that. Perfect. So I have m, I have k, I have I can just plug the entire thing in, and in fact I will. So delta T of freezing is equal to negative, 1 times the Ki is given as 1.86 degrees Celsius per molality, and my molality is 0.730 m. Okay, and once I do that, I get that I have negative 1.36 degrees Celsius. So my freezing point is lowered by that amount. So I'll try here. Freezing point FP is lowered by negative 1.36 degrees Celsius. But for water, the freezing point, the regular freezing point for water is 0 degrees Celsius. Therefore, my modified freezing point is negative 1.36 degrees Celsius. So you can see that once you add some sugar to water, the water will freeze at a lower temperature. And this is the principle of salting roads in the winter in places where it snows, not here in Florida, but places where it snows, because the freezing point of water will be lower. So just by adding salt to, say, snow or something, you get to melt the solution, because the freezing point would be lower. You can reduce it by quite a bit and get things to melt, and that's the rationale behind adding salts to roads. Okay, so let's do another example.